implementación de distintos algoritmos, el proceso puede ser, la verdad, de mucho consumo de tiempo. Referirse a que en el diseño tenemos una gran cantidad de parámetros de los cuales tenemos que decidir sus valores. Y existe una serie de técnicas o sincronizadores de parámetros que se han diseñado a lo largo del tiempo para poder automatizar este proceso. Entre ellos, los más conocidos son Paramilest, iRace, Evoca, entre otros. Y Thomas es parte del equipo que diseñó iRace. Thomas trabaja en la Universidad Libre de Bruselas y nos va a contar hoy su charla titulada Diseño automático de algoritmos, métodos y aplicaciones sobre algunos escenarios donde la aplicación de iRay se puede utilizar no solo quizás para considerar los valores de los parámetros, sino también incluso para decidir cuáles son esos o algunos componentes del diseño de esos algoritmos que se podrían desechar, por ejemplo, o que algunos son más importantes. Con Tomás, la charla va a ser en inglés, de todas maneras, Tomás me indica que puede realizar preguntas en español, no hay ningún problema.
No hay ningún problema, pero I speak in English, yeah? So it's so nice of you. Some things are in English, yeah? So this is automatic design of algorithms, methods, and first of all, an outline. So if it will be about the context what it is, and about automated algorithm configuration methods will be thing, and the thing will be automatic algorithm design, derived or previous, and including. And what one has to say is that the algorithmic solution of parameterization problems is one of the operations research and computer science success stories. Yeah? We have exact algorithm and the approximate algorithm. So exact or systematic search algorithms, they are branch and bound, branch and cut, constraint programming, and so on and so on. So on. They are there, and they are powerful. General software is available. Yeah, and the guarantees on optionality have been here, but it's often time-consuming or memory-consuming. On the other side, one has approximate algorithms. Yeah, so constructive algorithms, global search, meta-heuristics, and so on. And these typically are special purpose software. Yeah? So for an approximate algorithms, I have to implement. Yeah? And for the exact algorithms, I can download the software and run it. Yeah? And for approximate algorithms, you rarely have provable guarantees, but often they are fast and accurate. Much active research is on hybrids between exact and approximate algorithms. So you can think of meteoristics or something like this, materialistic, and so on. But what have these exact and approximate algorithms in common? Yeah? They have in common that the case high-performing optimizers, they involve a large number of sign choices and parameters. Yeah, and this is true for exact solvers and approximate solvers. Yeah, for exact solvers, you have design choices that include alternative problem already. Yeah? So pre-processing strategies, variable selection, value selection, branching rules, and so on and so on. Yeah? And many of these design choices, they have associated numerical parameters. Yeah? And we have here an example of the skip solver. So the skip solver, this 301, is not a recent one, yeah? But it was the one which we were thinking in about a paper in 2014. And then it has not 200, but it has 1,000 parameters on top. Yeah? And they said 1,000 seemed much for us. Yeah. Then we were in contact with the with the developers, and they gave us a list of 200 relevant parameters that influence the solver search mechanism. 200, yeah. So if you take CPLEX or Gurobi, they have about 100 parameters. Yeah? Approximate algorithms, you have design choices include the solution representation, operator, the neighborhoods, preprocessing strategies, and so on and so on. In many design choices, they have also numerical parameters. Yeah? And here an example is a hybrid SNS algorithm with about 500 plus parameters. And this I will show you, yeah, in the second part. The parameter types that one has is there are category parameters. So there is choice of the construction procedure, the choice of recombination operators, choice of branching strategies, and so on and so on. And one has also ordinal parameters, so the neighborhoods, lower bounds, and so on. Here we have, and then you have the numerical parameters. Yeah, so there are integer or real value parameters. There are weighting factors, population sizes, temperatures, hidden constants. Yeah, hidden constants are two. Yeah. So numerical parameters also may be conditional, yeah, to specific values of categorical or ordinal parameters. Yeah. So if you have simulated annealing as a local search, you have a temperature. Yeah. If you have a table search as a local search, you have the table list length, yeah, as a parameter. So these are different things. Yeah. And if one wants to know whether you do design or tuning calibration, one often has that the design is for the categorical and ordinal parameters, and the tuning calibration of the algorithm is the numerical parameters. So it's not 100%, but 95% or something like this. And what we have to do now is we have to design and configure algorithms, and this involves setting the categorical, the ordinal, and the numerical parameters. And only if you do all this, we do automatic design of algorithms. The design of optimization algorithms is challenging. Yeah? So it has many alternative design choices. You have non-linear interactions among the algorithm components and parameters and so on. And you have also performance assessment is difficult. So you need more than one instance to check what your algorithms do. Yeah? And the traditional design approach is to trial and error design very often. And this is guided by expertise and intuition. Yeah, but if it's guided by expertise and intuition, you're prone to overgeneralization because of what the experience you have with the TSP. You can take over to the QT, and this is not very good. So independent assumptions, limited exploration of alternatives. Yeah. The question is, can we make this approach more in principle and automated? Yeah, and obviously the answer is yes. If we go towards automated algorithm configuration, we apply powerful search techniques to design the algorithms. We use computation power to explore the design spaces. We assist algorithm designers in the design process and you make creativity for the higher level tasks. Yeah? But this we have to do. And if you have an automatic algorithm configuration techniques, you have the first thing that you have the parameters. Yeah, you have the parameters. These are the name of the parameters, type of the parameters, and possible values. If configurator. The configurator is the thing that also makes the automatic configuration. This configurator calls with a candidate configuration the software to be tuned. The software to be tuned is executed, returns a solution cost, and the configurator, based on this solution cost, calls again the things with a candidate configuration. Yeah, can be one candidate, can be various, but it's okay. Huh? And when the process is over, it returns the configuration to be used. Yeah, and that's it. Yeah, and the typical performance measures that one has is you maximize the solution quality. This is usually the thing that you take when you are this meta-heuristic. Yeah, you maximize the solution quality within a given computation time. And otherwise, if you are with exact algorithms, you typically minimize the computation time to reach the optimal solution of some other one. Yeah? But you minimize the computation. Yeah, this is already too hard. And now we come to the algorithm configuration tuning. Yeah? And the approaches that we have is, say, five things. So the experimental design is also, we have something, Calibra, for example. Yeah? But Calibra has 5 parameters. You cannot have 4, you cannot have 6, but you have 5, yeah, and various others. So very often these are ANOVA techniques or something like this. Yeah? You have numerical optimization techniques. So this is, for example, the math, which was done in 2006, and various others by Johan and Old. Also, this, which was also involved. Is where it has CMAES and so on and so on. Then very large kind of things are used search methods. You have a MetaKR, and the MetaKR is there of 1985. Yeah? And this is astonishing that Grevenstedt did this in 1985. But because of the computers were slow, yeah, it could not do it with quite some time. Yeah? And so it was Grevenstedt and was not considered. But then it went on. Yeah, this PARAM-ELS, genetic algorithms, linear programming, and so on and so on. And this is mostly of the years 2010 or something like this. So, yeah, what very started. Yeah? But this is also what goes on. For example, the NOMAD before, it's also in 2021. And another thing is model-based optimization, where you have, for example, a random forest, which gives you a nice, or can give you a very nice result. And well, the first one is SPO, then the SMAC. This SMAC is 2 is a Java version, SMAC 3 is a Python version, GTA, Rust, and so on. And the last one, where we have been doing some things, is sequential statistical testing, which was this FBase, which was one of the first algorithms, which was in 2002. And we then we have an iterated FBase, which is FBase in iterations for it, and a C-race to currently for better parallel configuration. And the general domain independence required are applicable to our variable types, multiple training instances, high performance, or it's scalable. And this it's true there exists some, but many of the things are not having these things. So that's it. Will now introduce the racing algorithms. Yeah? So we consider a set of initial candidates. So we have a set of candidates, and we consider a stream of instances. Yeah? And then we evaluate all the candidates on. There is the first instance, there is the second instance, there is the third instance. And as soon as we have some information how we can discard inferior candidates, we discard them. Yeah? And then so go on, the fourth, and we can also once again discard some, and so on and so on. Yeah? And this is repeated until a winner is selected or until the computation time is over. Yeah? And then you do it, yeah. And then you have here is the green result. This is what is the average. And if we would do something like uniform or something, we would have less results, yeah. And less results means that we have not the quality cannot be judged as good when we have many results already. Yeah, that's it. Yeah. And that's the racing method. This for the selection of the best configuration independent of the way the set of configuration is sampled. Yeah, and because of this, we can simply make it in iterated phrase. Yeah, so sample configurations from an initial distribution, and while we not terminate, we apply arrays, make array, modify the sampling distribution, and sample the configuration anew, and make this over and over. Yeah, over and over that. Not it's something like 8 times, 10 times. And the PyTrace package is it's also public. Yeah, it's if you want to use it, you can use it. Yeah, so it's implemented in R. And it's the iterated race is in R. It's flexible. You don't need to use R. Yeah, so you can just type it what your parameters are and run it. Yeah, and easy to use. So no knowledge of R is necessary. It has the parallel evaluation through the R things, adaptive capping for the for this one, the time varying one is good. This adaptive capping is very good, and also testing and so on and so on. Yeah. And the I-ray is shown to be effective for configuration tasks with several hundred of variables. Applications algorithm design. So we go now away from the methods. We go to applications of these things. Yeah. And here is an overview of applications of I-rays at NVIDIA. Yeah? So, so somehow this has started in 2007, 2009, and so on. And what we have done is we have done various combinatorial and continuous single objective optimization. But each time we do the full algorithm. So we have done something like 10, 15, 20 or so around it. What we have done also from the very beginning on is we have done it for combinatorial and continuous multi-objective optimization algorithm. So, for example, there is a Moaco algorithm for this. Is a MOEA, so a multi-objective evolutionary algorithm for this, and so on and so on. One paper is on anytime optimization, which I think it's something important for the meta heuristics part, because we don't start at we look at the result at 60 seconds, but you do it the overall thing. And you with the anytime optimization, you try to get at any time the best result. Yeah? So this is, and you have and another part is that you have the design of control software for example. Yeah? This you can also do. So, but the general approach that we are taking is that we have this design space definition, so the algorithmic component and the rules for the defining the components. We have here for a parameter space, we have the instance variable, and then we have also the database, in our case, the automatic parameter. One, and in the end, you have an effective algorithm. The main approaches that we have is top-down approaches and bottom-up approaches. Yeah? The top-down approaches, there are limited, so with 30, 40, 50 parameters, something like this. And if you have much more parameters, it's getting difficult. So, but in top-down approaches, you have developed a flexible framework following a fixed algorithm based on you apply high-performing configurators, and you have, for example, one of the earliest is Sappenstein. It's for the year 2009, but you have also our MOEA algorithms, solvers, and so on. So, yeah, you have the bottom-up approaches. They are this. You have a flexible framework implementing the algorithm component. Yeah? Contributes for proposing the algorithm. Yeah? And from components, for example, you represent them as grammar. Yeah? And then with the grammar, you have to frequently the usage of genetic programming and so on, but also use grammatical evolution, but with IRIX, yeah, and this is way better sometimes than genetic programming and so on. The only thing is that you have to reduce the number of times that you can do a recursion. So 2 recursions, 3 recursions, and so on. And this leads up to the automatic design of hybrid stochastic global search algorithms. Yeah? So the idea of this automatic design of hybrid stochastic global search algorithms, it's 10 years old, something like this. Yeah? But it has always improved. Development. Yeah? The approach is that we compose single objective SLS methods into components. This single objective is here done to have at least something. You can also have multiple so evolutionary algorithms. Yeah? So no problem. Yeah? Derive the generalized SLS algorithm structure. Yeah? So then you will see component. You have a component-wise implementation of the SLS algorithms. Yeah? And then you do the implementation. You present the possible algorithm compositions by a grammar. You instantiate a grammar using a parametric representation, and this allows to use the standard automatic configuration tools. Yeah, you can use Iris, MACD, whatever. And it shows very good performance when compared, for example, to grammatical evolution. This is a paper about paper was in IEEE Tech, yeah, and it's interesting that it's random search essentially, yeah, but which one didn't know, yeah, and this is yeah. So Iris was really better. And the general local search structure is an ELS. Everybody of you knows what the ELS is. It's this. Yeah? So we are with an initial solution. We afterwards do a local search. Then we are in the space of the optima. Then we repeat, we do a perturbation of the search, yeah, of the start. Then we do again on this modified solutions. We do a local search, and then we accept it, yeah, and we make this until a termination criteria is met.
So how we use the history on the perturbation component?
Yeah,
so looking for something similar?
No. The history is, for example, if you have DNS, yeah? If you can use DNS, you make search 1, search 2, search 3. And this is a little bit the history of the things. It's an ELS. So DNS is an ELS. Yeah? And here also the acceptance criteria. If you do it on each two, you have to have somehow the history, because if you do something like 1,000 iterations without improving, then you do some restart, then you have the history. Yeah? Oh, many SLS methods are instantiable from this structure. We see it in the next slide. Yeah? But the abilities that we have a hybridization. So we can use it, for example, double search, yeah, for the local search. Yeah? We have the recursion, and the recursion is here. Yeah? If the LS is chosen as an ELS, it's recursive. Yeah? We have an ELS inside an ELS. So we have recursion, and we have problem-specific implementation at a low level. And this, for example, is the example instantiation of some SLS algorithms. I have to say the SLS algorithms, you can say meta heuristics. It's more or less equivalent. So, for example, you have the SR, yeah, the simulated annealing. Yeah? You have no perturbation. The local search is a random move, and you have the multipliers that you have a simulated annealing. Yeah? The probabilistic iterative improvement is the specific temperature. Yeah? The double search is local search is the double search. Yeah? The ELS is here any, but it has to be. The iterative is the same thing as the ELS if it's using a local search. So it has a perturbation of the construct. Then it has also the possibility that you don't have a local search, and you have the acceptance criteria, and so on and so on. So, cool. And then you have to build the grammar. Yeah? So this is not the whole grammar, but the whole grammar perhaps are 2 or 3 slides. Then you have the grammar is the algorithm is equal to the initialization and then an ELS. The initialization, where you have this, then the initialization is random. So if you have a random initialization, you're done. Yeah? And also problem specific initialization, the ELS is a ELS, and you have a preferred local search index. And the third, the local search is non-initialization problem-specific perturbation, which are being defined down there. So the search is in ELS, and here is our recursive stuff that we send, simulated reading, and so on and so on. And the accept is always a grouping a set probabilistic thing that you want, yeah. And so the system overview is one has a problem specific problem independent grammar and a problem specific grammar. For this is a grammar code generated. It has a parameter instantiation. You have here the parameter instances, and then you have the parameter configuration. You take again the grammar to code in the opposite direction. You generate the source code to hide the code into an executable. You run it on some program instances and you evaluate it. And then what goes on and on and on. And in the end, one has an effective idea. Yeah? So this is roughly how it works. Yeah? And in a advanced system, we have the new C++ framework MED, or easily modifiable iterated local search implementation, that somehow supersides the previous work. We have the simplification. The previous work was done with Parallel, and it was removing the Parallel to get faster. There is no compilation anymore, and we do now a showcase on the permutation flowchart. And the system of the permutation flowchart problem is the initial solution, one has the acceptance criteria, and these two is the local search, the improvement in the neighborhoods, one has the perturbation, and one has the stopping part. So, and then these are different types of implementation. And if you have different types, so each one is a parameter. Yeah? So the experimental results we do, we generate a generic grammar for the objectives, makes then some completion time and total tardiness. Yeah, this we do. So we make a three objectives, and also one has to say that the flowchart problem or the permutation-based flowchart problems, they are like the TSP for routing problems. Yeah? For one obtains for each objective 502 is for the make span, 446 for the substitution time, and 481 parameters for the coded tardiness. There are some things that are not there for the substitution time. And this training set in all three objectives are 40 instances generated by Madelia. We have done something like 5 instances of each N for this one, and M is the 20. A flowchart problem has a number of jobs that are implemented on a number of machines. And one has 5 instances for each on 25 and 250 across 20 and 25 across 50. Yeah? And here it's set training set. Yeah? And this is very important. That was one implements something for a training set. It has really different results for the test set. And what is important is the test set, not the training. The test set. We use here for these experiments, which is for 502 parameters. Yeah, we use 200,000 experiments for iris. Yeah, one experiment is one configuration working on one instance. Yeah, one run of iris takes approximately 2 days of roll clock time, but it is on a roughly 100 cores. Yeah? plotted. Yeah, and that's it. Yeah. So we have here. It's important. Yeah. We have here different computation times. So we take tau equal 6, tau equal 120, tau equal 240, and this is 0.060 milliseconds times the number of jobs times the number of machines. And here is the best so far that one had before. And this is our that we obtained. And the results one sees are superior to the state of the art. Yeah? And one does it the same for the sum completion time, with the automatic configuration. These are all the results for the algorithmic time for this the one for the kernel-based one. This is the previous state of the art. Yeah, and it's better. And also for the things. Yeah, here is our previous good one, and this is better than all the other state of the art. Yeah? It's the new state of the art, or at least it was until the year 2009. And also we tackled the same three objectives with no idle and sequence-dependent setup times. Yeah? And here, always the red one is the one that we take for the second. Yeah? And here, in all 6 parameters where it was, it's the make span, this total complete time and the target test, it's the best one. Yeah? Here, the results are clearly superior to the state of the art. Yeah? This is the state of the art. Yeah? So if one has the closure problems with maximum objectives, yeah, does one have really a recursive iterated Kernighan or something, a recursive iterated over search? Not necessarily. Yeah? Here is the human made one, and here is the automated made one. Yeah? It's roughly the same, but the baseband here are the things that are important. Yeah? And if one wants to do it, here are the parameters that one needs for this one. Yeah? And if I have said before, these are the parameters, so 6 parameters. And this is rare for you have set for example, that is for field 502 parameters. Yeah, but many of the parameters are it's enough to have it in a few words. Yeah, and you will have much more if you have more parameters. Yeah? And this, yeah, it's true. But for example, for this closure problem with some completion time, it was that one had always one recursion. Yeah? It was the one where the first one was the first recursion, and here is the second recursion, and this is the thing. Yeah? Here is the automatic time, and here is the second time. Yeah, so it's 12 objectives overall. So once has a summary of the automatic algorithms for hybrid algorithms. Yeah. So the contributions are that one approach to automated design and analysis of materials, and it's not a silver bullet. Yeah. because the Silverlight would be not a major effort for the implementation. It is a major effort if one wants to have state-of-the-art. Yeah? But here, the state-of-the-art servers are also with respect to computation. Yeah? So this is important. Yeah? But it's not a Silverlight, but one needs the right components, especially the low-level program-specific ones. Yeah, so this I have to say. But for many problems in combinatorial optimization, for example, you have it. Yeah, you have it, and you can make it. If you want, one has it. If you make, yeah. And the current work for future work is the extension for other methods in place, the integration of other techniques, and the increase of generality tackling wide problems. Yeah? So this it's the summary of the and then why automatic algorithmic configuration. You have you have an improvement over manual methods for tuning. Since 10 years or something like this, I never do an algorithm myself for tuning. It's always algorithms. Reduction of development time and human intervention to increase the number of considerable degrees of freedom. Yeah? And I think this is important. Yeah? So that you do. Yeah? You have empirical studies for comparisons of algorithms. When you make an algorithm configuration, why do you take the parameters that someone invented? Or if you take, for example, a different problem, yeah, why? You have to use iris or SMAC or something like this. And it's a protocol for end users of algorithms. And this also, well, if you see this, well, a cluster is something small if we have it in the cluster. Yeah? So Leslie has 9 cores in this. Its automatic design is feasible. Yeah? So we have a paradigm shift in algorithmic development. And I would say in the algorithm development, in 10 or 20 years, I would think that everybody uses automatic tools. Configurable array frameworks in the large scale, it's very large things. It's larger than this what has been presented here. And the solving is a model of in the configuring for the parameters and the search with the parameter. And many challenges remain for proper representation, algorithmic structure, algorithmic components, and generation of components, automatic configuration techniques, and extensions to other techniques and challenging problems. Yeah? With this, I'm happy to answer questions.
We use some tools here generated instead of the individual domain. Why use source code generator instead of the individual domain implementation?
Why we used it in Docker Parallel Zero?
Una pregunta en español.
No,
okay. ¿Por qué usar un generador de código en lugar de un embebido el lenguaje de dominio? Sí, el embebido domain specific language. in the diagram, use a source code. Or more, he used source code. Compare the grammar to code. The code is a C++ code. When you use embedded domain specific language instead of the source code generator.
Yeah, domain specific language. Or, if it's not compiled, it's slow usually. Yeah, 50 times slower, 100 times slower. So, and if you have 100 times slower, this reduces the time. But it would be also peaceful if you have time. So you would know.
¿Una pregunta? No. I understood your talk. Very nice talk. But you need, in order to approach to a problem, you need some algorithm before. And the main result of your research is about tuning some parameters concerning this algorithm. But first of all, you have to have some algorithm to solve a particular problem.
Yeah, but it can be a very general. It's
could we take an example, for instance, the traveling sense? Yeah. There are many approximate solutions, and so you start from those solutions in order to obtain a better solution of your algorithms. Is that the idea?
Not necessarily, yeah. So here this is done for getting state-of-the-art results, yeah. But if I don't want to get state-of-the-art results, and if you why does one do this these algorithms? Because somebody else wants to do it in practice. Yeah? I would be my thing, yeah? And if you have these things, you even can do, for example, if you search something like constructive heuristics, you could design the things for the constructive heuristics. What is the approach to take from the constructive heuristics? It's only here because it's state of the art. Yeah? If it's not, well, one has to have an algorithm or something, yeah? But it can be really very general.
Yeah. But there are many problems in mathematics for which there is no known algorithm. There are problems, but there is no known algorithms to solve that problem. In that case, it would be very nice to have a method to produce algorithms to solve at least approximately some of these problems.
For example?
Well, say the twin primes conjecture.
Yeah, okay, but this is
ideal infinity.
Yeah.
You know that.
Yeah.
So there is no algorithm.
There's no algorithms, but this is not. Yeah, I have to say that I'm in combinatorial optimization, yeah? And everything for in combinatorial optimization, which is not infinite.
Yeah. You have to work with finite problems. Yeah. And another question. You talk about grammars, and you show us the productions of some grammars. how do you use that? It is because one should check first that the
Yes.
productions of your
They are,
grammar,
they are checked. they
they are
are
not
checked.
contradictory.
No, they are checked. So,
Yeah. So
the
you need
thing is,
another algorithm to do that.
yeah, no, but they are checked by the health with the humans, yeah. And then also there are one takes it. This this, this is the initialization, the local search, and so on. This is all there that one can do it. So it's not a problem.
It's possible to do by hand.
But again, you can also do by hand if you have the time.
You have so many productions. This is
Yeah.
also that can explode.
No, it can also only explode if you don't take care with the version. Otherwise, it's final. Yeah? And with a recursion, it's taking care that you have maximum. Yeah, I would. This thing was achieved recursions. Yeah.
And what is the idea behind these grammars? You are using that grammars in order to change parts of given algorithm?
No, in order to generate it.
Generate.
Yeah. So so you start by something. Yeah, you have to start by algorithm. Yeah, and this is the only way how you can start. And then you have to do initialization. The initialization can be random. And if you have random here, you're done. You don't have any more initialization. And if you have a problem specific initialization, yeah, then not here. But this is it. Yeah. So the problem is that specific initialization is something else in the random and they're done. And you have done the ELS, and this is and this you can do, then it's done.
I have a question related. You can have, for example, in the grammar that you can have different neighbor structures, and you can change the order that you are visiting.
Yeah.
Because maybe you can change the search space region that can be visited.
So this is one of the VND or
Yes.
there it's this is not an IRIS specific thing to treat it, but it has to be made well, not by heat, but it's difficult.
I have another question. You were working with the permutation closure. How costly can be, for example, to adapt this general component to another problem? Once changed to TSP, I imagine that there are some problems.
No, we have changed it already. So we have for vehicle routing problem, for example, the thing for Leslie is in vehicle routing problems. But he has different local searches and so on. It's a problem that if you want to have really state-of-the-art results, then you have to do it takes more time, so much more time than I implemented now something for the bigger. But it's feasible. So this was a thing that was in one PhD. And it's done.
¿Alguna pregunta más? Santiago, ¿tenéis preguntas? No. Pues muchas gracias.
Gracias.